Hello my fellow developers, let's learn together how we build generative AI applications in Java by using the Spring AI framework and Postgres pgvector extension. We will start with the basics. I will show you how you can deploy a database instance with the pgvector extension on your own machine. Then you will see how we use Spring AI to generate embeddings for user prompts and perform vector similarity search by using those generated embeddings and the data stored in your database. And we will conclude by discussing several ways on how you can scale your Gen AI apps in Java by creating specialized indexes for the vectorized data or by migrating to a distributed version of Postgres. Let's not waste a minute and do this deep dive. Alright, let me introduce you to our sample application that we will be using today for our little experiments. This application is a lodging recommendation service for those traveling to San Francisco. Imagine that you're heading to the city and you're looking for an apartment near the Golden Gate Bridge with a nice view of the bay. Why not? All you need to do is to type in a prompt like this and then click the search button. And after that, the application takes this prompt and sends it to the OpenAI GPT model to provide you with the most relevant recommendations. And it takes time, right? So before we discuss what we are going to implement with Postgres pgvector, let me show you how this mode that uses OpenAI GPT model is implemented with Spring AI. Jump into the application source code. And by the way, in the description to this video, you will find a link to the application's repository on GitHub. So you will be able to reproduce all the steps on your own. Let's start with the PAM.xml file. Here is the most interesting dependency for today, Spring AI. Spring AI is a new framework that simplifies development of generative AI applications in Java. It supports multiple LLMs and models, including the famous OpenAI. At the time of this recording, Spring AI was under active development, and it was required to include the Spring Snapshots repository in your PAM.xml definition. But when you will be watching this video in distant future, this requirement will no longer be needed. So check the latest version of Spring AI. Next, once you define the dependency in your application properties file, you also need to provide your OpenAI API key. And you need to pick the OpenAI model. I'm going to use GPT-4, you can use GPT-3.5, or you can use future models that will be created by the company. And finally, the application uses this chat service implementation. We are using the ChatClient of Spring AI. And the chat client supports several messages. It has a system message where you explain to the neural network what's expected for it. For instance, I'm saying that, hey, you're an assistant who helps people to find lodging in San Francisco. You need to suggest 3 options and send back a JSON object in the following format, okay? So that's my system message, that's my requirement. Then, when you're typing in that prompt in the application UI, the backend executes this search places method. We are taking this user prompt, we are also adding the system message to the prompt, and after that we are using this AI client to generate the response from the OpenAI LLM. Once this response arrived, we convert it to the JSON, and then you can see it on the interface of your application. This is how it's implemented. But what's wrong with this implementation? You know, it's just slow. It takes so much time to generate all these recommendations that it will not work for most of the applications. Let's see this one more time. Refreshing this UI, typing in the same prompt, and now start counting. 1, 2, 3, 4, 5, 6, 7. It will take more than 10 seconds to generate all those recommendations because the search was happening across the deep and broad knowledge base of the GPT-4 model. But imagine that you work for a company that has its own data set for properties for rentals. Think about Airbnb. Now you can take that data set, store it in Postgres, generate embeddings for the properties descriptions, and perform the vector similarity search using Spring AI. That's why the next step for us is let's deploy a Postgres instance on our own laptops with the pgvector and then load the sample Airbnb dataset for San Francisco in the database. After that, we will create the version of this application called Postgres Embeddings that will perform much faster. Presently, when you're doing the search using that mode of the application, nothing happens. Why? Because we need to implement this mode using Spring AI from scratch. And let's start with Postgres deployment. I'll deploy Postgres in Docker, and because of that, I will create a special directory called Postgres volume on my host operating system, all the Postgres data will be stored in this location, and that will allow me to restart my container without losing any data. Next, using docker run command to create our container, we will name it Postgres, and then we can provide additional parameters. For instance, that's going to be my Postgres username, that's my password. I will be connecting to this Postgres instance from the host using my application and data grip tool. That's why I'm exporting this port number. That's the volume that we have just created. It will be used for the Postgres data. And finally, we are using this image that comes with the pgvector extension. That's what we want to use for our development today. Done. So the container is up and running. Next, our application comes with sample dataset of Airbnb properties in San Francisco. Now I will use docker copy command to copy the schema of this Airbnb table to my Postgres container to the home directory. Let's copy it. After that, I'm copying the dataset to the same location in the Postgres container. And it takes time because this file is large. It already comes with embeddings that were pre-generated for the Airbnb descriptions. All right, all the files are copied to my Postgres container. And the next step is to connect to Postgres container using the exec command and to start the PSQL client and ask that PSQL client first to create the table with Airbnb listings. Let's do that. And also that file enabled the pgvector extension. I will show you it later. Once this is done, we will repeat the same step. We will connect to Postgres container. We will start the PSQL client, and then we will ask this client to copy the data with the embeddings into our Airbnb listing table. And now it will take more than a minute because we have more than 7,000 Airbnb properties and every property has an embedding associated with it. So let's wait. Done. The data was loaded into the database. Now, how about we use data grip to take a look at the structure of this table and the data set. Connecting to this Postgres instance, let's refresh this connection. Going to the Postgres public schema, and here is under the tables, you can find this Airbnb listing table that we have just created. And take a look at this, it already has more than 100 columns. Next, let's run some SQL. Opening a new query console. And first, I want to show you that the pgvector extension was in fact installed and enabled. For that, you need to make a call to the pg extension table. And here is our pgvector extension. When you are enabling this extension from scratch, all you need to do is to run this create extension command and vector. So now it said that the extension already exists, which is expected because this statement was defined in our schema file that we executed previously from the command line. All right, going back to our Airbnb listing table, it has several columns that are needed for our application. The first one is Airbnb property name, then description, detailed description, and also description embedding. This description embedding is generated from this textual representation of the description. We are requesting this from Airbnb listing table, and let's take a look at this at 3 different properties. Alright, so here is how the information looks like. That's the name of different properties. Then you have a very long description with different amenities. And then for every description, you have a multi-dimensional vector that was generated by the OpenAI embedding model. So we have all the data needed in the database. What's left? Now we need to jump back to our application and use Spring AI to implement the logic that will be doing the search over this description embedding data. Finally, we are back to the application logic. Before we start coding, let's go to the PAM.xml file and make sure that we have the Postgres dependency here. Alright, cool. We have the Postgres JDBC driver defined as a dependency in this PAM.xml. Also, in the application properties, I already defined Spring data source, URL, username, and password for my Postgres container. That was done. Now we need to go to the embedding service class that has to be implemented. We just need to provide the implementations for the following methods: search places. The user types in the prompt and you need to generate a list of recommendations. This time though, we are going to use the EmbeddingClient of Spring AI framework to generate a vectorized representation of the prompt. And once that vectorized representation is generated, we are going to run a vector similarity search request over the data stored in Postgres. That's why we need this JdbcClient. Let's generate the constructor, and we want to outer wire the following two objects. That's why we are placing their outer wired annotation. Done. Now let's get down to the implementation of the search places method. Let's start with the user embedding. We have this AI client, embedding client of Spring AI, and it has several embed methods that can take your textual representation or any other document and generate a vectorized representation for this data. We have the user prompt, and we want to get a vector that corresponds to this user prompt. In return, the method will give us a list of floating point numbers, the vectors stored as doubles. So what happens internally when you execute this method? Spring AI will make a network call to the OpenAI service, and it will be using the OpenAI embedding model to generate this embedding for you. Eventually, it's still a network call that happens here. Next, we need to write some SQL. We have our JdbcClient that has the SQL method. Let's generate this statement spec, and we will create the following SQL command. We need to select the name, description, and the price of every Airbnb property. We are getting this data from our Airbnb listing table, where the condition we want to get only those listings that correspond to the user prompt. And we are going to perform the vector similarity search. We have this description embedding column. We need to calculate the distance between this column and the user prompt embedding. We will pass it as a parameter. And we are giving a hint to Postgres that that's of the vector type. Here is we are calculating the cosine distance between these vectors. The cosine distance is an angle between your vectorized data. The smaller the angle, the more relevant an Airbnb listing will be for the provided user prompt. However, it's always easier to operate on the similarity. You can convert this distance to the similarity by subtracting it from 1. The similarity is some value in the range between 0 and 1. And the closer the value to 1, the more relevant the result will be. I will use this 0.7 similarity. Next, you also want to order your data. You want to order by description. First, you want to get those that are the closest to the user description, and we want to get just 3 different recommendations. Finally, we need to pass our parameter for the user prompt placeholder, and we need to use this embedding that we just can convert to string. Done. Next, we are taking this SQL query and the query method of the JdbcClient, asking it to convert the result to their object class, to the places. We are getting a list of objects. So that's it. What we need to do is to return this value, and we no longer need this method call. Okay, that's a complete implementation of our embedding service that uses Spring AI EmbeddingClient and Postgres pgvector extension to find the most relevant Airbnb listings for the user prompt. Now, let's restart our backend, starting it up. Ready? Going back to our application, let me refresh the screen just in case. We are selecting the Postgres embedding mode that we have just implemented and clicking the search button. And look, it just takes a second. It takes less than a second to provide you with all of those recommendations. And when you click the search button first, the application makes a call to the OpenAI embedding model to generate an embedding for your user prompt, and then it does the vector similarity search within your Postgres container. Wonderful, right? What's next, my friend? Let's talk about optimization and scalability. How can you make this application scalable? So right now, what's happening? When you do the vector similarity search, we take this user embedding and we compare it to all the embeddings stored in the database, and that's a sequential scan. However, as of now, you don't see any bottlenecks or latency issues, because we store a little bit more than 7,500 Airbnb properties in the database. And one of the obvious optimization is to create a specialized index for our vectorized data. Let's see how it works. We are back to our application logic, and before we create that specialized index for our description embedding column, what I want to do is to show you the actual execution plan that is generated by the database. For that, we will create this analyze statement. Then we will just run this request, we will get a list of rows, and we will print the execution plan to our terminal window. We will update this return method as well, because right now our application is not going to get any records. We just want to see the execution plan. Let's restart the backend. Then jumping to our application, running the search. It's expected that we don't see anything right here, but if I go back to my terminal, you will find this execution plan. What we are searching for is for the sequential scan. Here it is. It said that we are performing the sequential scan over the Airbnb listing table. And again, that's not a problem right now because we are searching through 7,460 rows properties stored in the database. But imagine if you store thousands or millions of embeddings, it's gonna become a bottleneck. Now let's create our first index. Jumping back to DataGrip, where we already have a connection with our database, and let's create the index on Airbnb listing table. We need to use a specialized index. The most famous index at the moment across all vector databases is HNSW. It stands for Hierarchical Navigable Small World Index. It's also supported by Postgres pgvector. We will build this index over the description embedding column using the vector cosine distance operation. We use this cosine distance calculation method in our application logic, and we need to use it also for our index. Alright, ready, let's build this index. And it will take time to build this index. I'm not going to go deep into the details of it, but all you need to know is that right now you're creating a multi-layered graph of interconnected vector points. If you want to learn more about this index, watch one of my previous videos on this topic. You will find it on my YouTube channel. Excellent, the index was created, and you can find it under the Indexes tab in DataGrip. Here it is. Going back to the Visual Studio Code, and let's clear this screen and execute the same user prompt one more time. Jumping back to the Visual Studio Code, if you search for the sequential scan, you will no longer find it. Why? Because right now the database performs the index scan, right? It uses our index that we have just created. And this is how you can improve the performance and latency of your GenAI applications in Java. What's next? Let's talk about scalability and availability of our GenAI application. Presently, we store the entire dataset in a single database instance. And this is fine as long as the dataset is relatively small and we are in early days of the development. However, in production, we might end up storing hundreds of thousands or millions of embeddings, and those embeddings can occupy gigabytes and terabytes of the storage space. Plus, apart from that, we don't want the database to be a single point of failure. That's why some of you might want to have Postgres that scales and never fails. One of the solutions in the Postgres ecosystem is YugabyteDB. YugabyteDB is a distributed SQL database that is built on PostgreSQL source code. It's literally distributed Postgres. I already have an instance of YugabyteDB running on my local laptop. Let's open the UI of the database that is on port number 15433. Here, as you can see, that I deployed a 3-node database cluster. I also use Docker for that. And to shorten the time, I pre-created the same Airbnb listing table and preloaded all the data, including embeddings. You can see that the data is sharded, and every node of the database stores a subset of the data, which means that you can scale linearly and horizontally. And you scale not only storage-wise, but also all the read and write requests are going to be distributed across these nodes. From the high availability standpoint, if any of these nodes goes down, it's not a big deal because the other nodes store replica copies of our data and they will continue serving your application request without any outages. Okay, so what do we need to do from the application standpoint if you want to switch from Postgres to YugabyteDB? Remember, I said that YugabyteDB is built on Postgres, is distributed Postgres, which means that for this application, we don't need to introduce any code level changes. We just need to change the connection string, and that's it. Let's do this right now. I need to restore the initial implementation of our embedding service client, because you remember that we used this explain analyze method to see that we are using the index. Yeah, we no longer need this, we just want to get the data. Ready, this is our initial implementation of the search places method that we use with Postgres. And now we are ready to switch to YugabyteDB. All we need to do is go to the application properties file and update the database configuration settings. YugabyteDB also uses Postgres JDBC driver, no any changes here. YugabyteDB listens on this port number 5433. We are connecting to the first node of the cluster, and that node then will be able to distribute requests across other nodes. We will connect to the database under the name of YugabyteDB, and the username is gonna be Yugabyte and the same password. That's it. That's all you need to do if you want to switch from Postgres to a multi-node YugabyteDB cluster. Let's go to the application and let's restart our backend. All right, starting it up. The application successfully connected to YugabyteDB using the Postgres JDBC driver. And now if you go back to the application UI, let's run the same prompt. And you can see that you're getting the same data, but from your multi-node YugabyteDB cluster. Job done. How do you like this, my friend? Isn't it cool? You can use Spring AI with the Postgres pgvector extension to build generative AI applications in Java that scale and never fail. And in the description to this video, you will find a final version of this application. So go grab it and reproduce all the steps on your end. And keep mastering databases. Bye bye now.